Hey Pre-Calc students, in this video we're going to talk about function features and their representations. So the first thing is there's different types of functions. Functions have different types of names. Like for instance, I can name a function a linear function. I can name a quadratic function. And there's many other different types of function names. Pause the video and see how many names you can come up with that you studied from Math 1 all the way up to Math 3. Okay, here's the total list of all the functions you've been exposed to from Maths 1 to Maths 3. So we have linear, quadratic, cubic, exponential functions, logarithmic functions, sine, cosine, and tangent, also known as our basic trig functions, the absolute value function, the square root function, and the rational function. Is there any that I left out? Let me know in class. Okay, the definition of a function is any relationship that maps an input to an output. Functions can be represented in 4 different ways. So I've got the same function down below being represented in 4 different types. So the first type is verbal. Verbal is usually when we're talking about a word problem. So we got Tony who deposits $115 into a savings account. Each week thereafter, he deposits $35 into the same account. So in the very first week, he has deposited $115. Again, here's the verbal representation of what's going on. The numerical version of what's going on, or the numerical representation, is also sometimes known as a table representation, where we have the input, which is the number of weeks that is happening, and the output, which is the amount of money. I'm going to write that down. Okay. The next thing is that once we have a table representation of a function, we can create a graphical representation of that function. Normally we put the input along the x-axis and the output along the y-axis. So again, we're seeing this rate of change here every week after we're doing $35. So our table is increasing $35 for every week that's happening. You can also see that on the table. So as the weeks go on, well, in the very beginning, we start with $115, and then we're increasing $35 each time. Again, we're talking about the same situation, just different ways to write it. And then to talk about this algebraically, we can say, well, we can write a function in terms of W being weeks, and we can say that, well, we start with $115, and then for each week, we're going to add $35 per week. We're going to add that onto the $115. So here's an algebraic representation of that same function. Again, functions can be represented in 4 ways: verbal, numerical or table, graphically, and then algebraically. Because not all functions are alike, we have linear, quadratic, sine, cosine, all of these different functions. Because they're all different, we want to be able to describe the features of them. Here's a total list of all the features of a function you're responsible for being able to identify. Most of these you have learned before in a previous math class. I'm going to focus on some of the new ones. So domain and range are ones you should have learned from in the past. Relative minimum and maximum versus absolute minimum and maximum. I'm going to do a little bit of a key off to the side. So if we're talking about a relative minimum, okay, so for a relative minimum, a great example of a function that has a relative minimum would be a cubic function. So a cubic function can kind of curve like this. So this point right here is what we would call a relative minimum. And the reason why we would call it relative is because of the fact that this function goes down to negative infinity. It does decrease forever. So this little like saddle point kind of like dips like a little minimum value. We call it a relative minimum. An absolute minimum would be like a quadratic. A quadratic where the ends go up, this would be an absolute minimum. So again, the difference between a relative and an absolute. Absolute means it is the lowest point on the function or the graph, and a relative means that it looks like a minimum but maybe isn't the absolute lowest point on the graph. Intervals of increasing, decreasing, positive, and negative you should have seen before. Same with x-intercepts and y-intercepts. Points on a function, so defining x and y values on a function. Types of asymptotes. There are two types of asymptotes. There are both vertical and horizontal. In behavior of the function describes the arrows, and then concavity is also a new one. So I'm going to show down below the difference between, what is concavity and what's the difference. So there's two types of concavity. There is concave up, and concave up is describing anything that is curved in an up-like fashion. For instance, a quadratic, a positive quadratic, is going to be curved upwards. So this is concave up. To concave down means to curve downwards. So like a negative quadratic, which would flip it upside down, this is kind of curved in the downward fashion. This is what it means to concave down. So we're deciding, is a function have concavity, and if it does, what type? Is it concave up, concave down, or does it have a mixture of the two? Okay, we have the given representation of a function. So looking down below, I have a table version of a function. We want to find the other representations. So we have the table. We're not going to create an equation, we're not going to create a verbal representation, but we're going to create a graph representation, and we're also going to create a algebraic representation or an equation. Pause the video and see if you can plot the points and create the graph on your own. When you're thinking about the graph, it does say a continuous function. So when you have a continuous function, you want to connect the points, creating one smooth continuous line. So connect all the points that you plot. Okay, I have my graph created. I'm also going to go ahead and give this function a name. I can see by the graph, and I can also see by the table that there's a constant rate of change. For every 5 units of x, I'm decreasing a -6 units for y. So this is creating a linear function because it is a constant rate of change. So this is, again, as a linear function. Okay, I've got my graph. I'm going to create an equation. So it's already telling me that f of x is equal to, well, I'm going to start with 35 because that's my y-intercept, my starting value, and then I'm going to subtract 6/5, my slope, for every x value. Okay, this is my equation. Now our goal is to identify all the features that we talked about in our last slide. So I'm going to take a second and I'm going to get myself organized to have a list of those features. Okay, first we'll talk domain, range, min, and maxes. Okay, so for my domain, the domain is all x values that the function covers. Because the function is continuous, it will eventually cover all x values. It will go backwards into -infinity. It will go forwards until x's reach +infinity. So my domain of this function is either, you can say all real numbers, or you can use -infinity to +infinity. You can also see that the range is going to do the same. So it will increase up to +infinity and decrease down to -infinity. Again, the range is your y values. So we're going to go from -infinity to +infinity. Since the range of this function is going all the way down to -infinity, the y values go to -infinity, and the maximum goes all the way up to +infinity. There's no min or max, and because this doesn't have any curve in it, there's not going to be like a relative min or max. So we have no mins and maxes in this function. The next thing that I'm going to find is my x and y intercept. My y-intercept I can see by looking at my graph. The y-intercept is at 0.35. The x-intercept I can't tell by my graph, so one way you can always find an x-intercept is by setting your equation equal to 0 and solving for x. I'm going to write my x-intercept as a point, so the x value will go first, 0. That would mean if I were to extend this line, it would cross the x-axis at this point. Next, we're going to talk increasing, decreasing, and positive and negative. Whenever you're describing these, you always want to talk about it in reference to the x-axis, so the domain, and we always read this left to right. So I'm going to start over here at negative infinity, and as I move towards positive infinity, my function is only decreasing. So there is no place where the function is increasing. So I'm going to put none. And since it's decreasing over the entire domain, I'm going to actually write the domain from negative infinity all the way to positive infinity. The function is positive before its x-intercept. So again, the function will have positive values. It will have positive output values all the way up until it hits that x-intercept. And so the positive values of this function happen from negative infinity up to that x-intercept. And it has negative values after the x-intercept from 29.16 repeating to infinity. Linear functions have no asymptotes, so we're going to write none. And because linear functions are straight lines, they have no curve in them, so they also have no concavity. The last thing that we'll talk about is the end behavior. And the end behavior is talking about what happens when x approaches infinity. So as x approaches infinity on my function, as x approaches infinity, this function is decreasing to negative infinity. So we'll say that the f of x is approaching negative infinity. And then on the other side, as x approaches negative infinity, as x is approaching negative infinity, that function is going up to positive infinity. So f of x is approaching positive infinity. That's all the features for this linear function. Make sure you have them all. Okay, so for this next example, a lot of the work is going to be done off screen, so you'll want to pause the video when I give you time to do so. We have another function, let w of x equal 200 times 0.5 to the x power. Because I have to the x power, this is called an exponential function. Pause the video, and I want you to fill out the table and create a graph that goes with your table. Okay, check your table and your graph. Make sure when you're setting up your graph, you're using appropriate scale. So every time I went 800, I went halfway down to 400, halfway down to 200, halfway down to 100, halfway down to 50, and so forth. This is what is called a decreasing exponential function because it's decreasing by a half each time. See if you can pause the video and find the domain, range, min, and max. Our domain of our function can be any number, right? I can extend my domain to negative infinity. I can extend my domain to positive infinity. So my graph covers the entire x-axis. However, the range, as I continue to decrease in my y values, I do have a limit, or I do have what's called an asymptote in this function. So each time I take half of the values, I'm getting closer and closer and closer to approaching the y value 0. So my range is going to go up to 0, but I'm using a parentheses to say that my range does not include 0. My mins and maxes, again, because it can go up on the left side, it's going to have no max, and then because of this horizontal asymptote here in the graph, it's also going to have no minimum because it will continue to decrease. It will just decrease and approach 0. See if you can do your x and y intercept on your own as well. Again, there is no x-intercept because of that horizontal asymptote. It's going to approach the 0 line, but it will never reach there, so I have no x-intercept. My y-intercept is 0, 200. Next, I want you to try increasing, decreasing, positive, and negative domains on your own. Again, these ranges are talking, or these domains are talking about domain. So as I increase on my domain, my range is decreasing. So I only have a decreasing function over the domain. Same thing with positive. As I go from negative infinity to positive infinity on the x values, my function is only going to be positive. So positive from negative infinity to positive infinity, and I have no negative values. Again, these are all talking about the y values, not the x values. The x values are what we're describing in the parentheses. The increasing, decreasing, positive, and negative is talking about the y values. Okay, so the reason why we have no x-intercept, the reason why our range stops at 0 is because I do have a horizontal asymptote. And the equation of the horizontal asymptote is y equals 0 because that's the value that we're approaching but never getting to. This graph is curved in the upwards direction. So this is curved, but it's kind of curved going up instead of kind of curved going down. So this is concave up. And the end behavior of this graph, as x approaches infinity, the y values are approaching 0. And as x approaches negative infinity, the y values are approaching infinity. Again, just showing that on the graph. As x approaches positive infinity, the y values are getting closer and closer to 0. As x values approach negative infinity, the y values are going up to positive infinity. For this last slide, we have a quadratic equation. I would like for you to try all features on your own and pause the video, try it, and then come back and check your work. Okay, check your work and see how you did. There are a few things in my work I would like to point out. So the first is my bracket on my range. Because this function actually goes to -4 is going to be included in the y values. So my range is starting at -4 and then it goes up to infinity from there. So again, my range is starting there at -4. That point, -1, -4, is in a minimum value and it is included on the quadratic equation. Unlike 0 on our exponential equation where we approached 0 but never got there. My two x-intercepts you can read from the graph, and the y-intercept I read from the graph as well. For my increasing, it's really important to understand that when I'm talking about increasing, I'm talking about where the function is increasing. So starting at -1, the y value, the function increases from there. And it decreases before that 1 value. So it's decreasing until that 1 value. So from negative infinity to -1, we see from negative infinity to -1, negative infinity to -1, it's decreasing. From -1 to positive infinity, it's increasing. When I am talking about positive and negative, I'm talking about where the graph is positive is when the graph is above the x-axis. So it is positive above the x-axis, and it's going to be negative when it is below the x-axis. So using your x-intercepts as places where the function switches between positive and negative. So again, it's positive from negative infinity to -3. So negative infinity to -3, and then it switches to negative from -3 to +1. And then it switches back to positive from 1 to infinity. I'm using a union to connect my two positive sets of numbers. I have no asymptotes in this graph. This graph is concave up because it's curved upwards. And then I have my end behavior. Both ends of this function are going up. So whether I approach positive infinity or negative infinity on the x-axis, my function is going up. That's it for this video. We'll practice more of this in class. Over the next couple of days, it's important for you to decide what features you have questions about and you would like more help on.